Welcome, listeners, to The Deep Dive. Today, we're plunging into a really fascinating area of artificial intelligence. It's all about making powerful AI accessible, efficient for everyone.
That's right.
You've sent us a stack of sources on AI model distillation, and our mission really is to pull out the most important insights, maybe give you those aha moments, and, well, turn some complex ideas into clear understanding.
hmm
Think of this as your shortcut, to being genuinely well-informed about how AI models are getting smaller, faster, and, well, smarter. We're really focusing on that common challenge in AI today.
Yeah, the big models.
Exactly. These incredibly powerful models that are often just too large or too slow, maybe too expensive for everyday use. How do we actually get that advanced AI everywhere we need it? On our phones, in our cars, even those tiny IoT devices, the smart sensors and gadgets connecting everything.
It's a crucial question, absolutely. And this deep dive will explore precisely how we bridge that gap. The gap between cutting-edge AI research and, well, practical widespread deployment. It's really a strategic advancement. It addresses the very real computational demands of modern AI, making sure that AI's impressive capabilities can actually be used out there in the real world, not just stuck in massive data centers.
Okay, so let's unpack this fundamental concept then. AI model distillation. What exactly is it, and why has it become, well, so crucial in this rapidly evolving world of AI?
Well, at its heart, AI model distillation is a technique. It's where a large, complex model, it's called a teacher, transfers its learned knowledge to a smaller, more efficient student model.
Okay, teacher, student, got it.
Its primary goal is really to tackle the escalating computational demands of these complex AI models. It's about making them more efficient, faster, and, broadly accessible for deployment. This isn't just shrinking models. It's about smarter, more focused learning.
So it's almost like a master chef, the teacher not just handing an apprentice a recipe book, but actively passing on their nuanced understanding of why certain techniques work, like the subtle flavors, the intuition.
That's a great analogy. Yeah. The apprentice, the student model, learns the why behind the cooking techniques, not just the what.
Okay, makes sense.
And this concept, this idea of model compression, it actually goes back quite a way, back to 2006 with pioneers like Mihai Christian-Busila and Rich Caruana.
Oh, wow. So it's not brand new?
Not brand new, no.
But
But it was truly formalized, or maybe brought into the mainstream, in 2015 by Google researchers, folks like Jeffrey Hinton, Oriol Vinyals, Jeff Dean.
Right, the big names?
Exactly. And that's when it really gained traction, especially as neural networks just started their, well, explosive growth in size. The computational cost just became prohibitive for so many applications. It created a real bottleneck for widespread AI adoption.
And that's where we get to the really profound aha moment of distillation, isn't it? It's more than just a technical tweak.
Oh, absolutely. Think about DeepSeek's R1 chatbot. What they demonstrated wasn't just technical wizardry. It was like a seismic shift in the AI power dynamic.
How so?
Well, before, advanced AI often felt like this walled garden, right?
Yeah.
Accessible mostly to the tech giants with, massive compute resources.
Sure.
But DeepSeek, a smaller Chinese AI startup, they developed this advanced AI model with significantly fewer resources, heavily leveraging distillation.
Okay.
And this achievement, it apparently roiled the stock market and really woke the AI world up to distillation's transformative power. It showed how a smaller entity could suddenly compete, go head-to-head, armed with clever techniques instead of just endless computing power.
Wow.
That's the insight. Distillation is democratizing access to cutting-edge AI. It's potentially reshaping the entire industry landscape, fostering a more decentralized AI ecosystem.
That's a huge shift. So, okay, how does this knowledge transfer actually happen then? It sounds much more sophisticated than just like copying the teacher's final answers or even its architecture.
It's far more nuanced than just simple mimicry, yeah.
Yeah.
The key lies in what we call soft predictions or soft target.
Soft predictions.
Yeah. So unlike hard labels, which are just binary correct classifications, like saying, this is a dog, with 100% certainty soft predictions, are the teacher model's probability distributions over all possible classes.
Ah, okay. So instead of just saying this is a dog, the teacher might say, okay, I'm 90% sure it's a dog, but maybe 8% sure it's a wolf, and I don't know, 2% sure it's a fox. It's revealing its whole thought process.
Precisely. Its internal confidence, its uncertainties across all the options. And this leads us straight to dark knowledge, a term Jeffrey Hinton actually coined.
Dark knowledge. Sounds intriguing.
It is. It's the rich, implicit information embedded within these soft predictions. It captures subtle relationships and confidence levels that go way beyond just a simple correct answer.
Okay.
This dark knowledge helps the student learn the underlying reasoning, generalize better. Think of it like this. The teacher knows a dog is more similar to a wolf than it is to, say, a sandwich.
Right. Obvious to us, but the model needs to learn that similarity.
Exactly. That subtle relationship, that hidden connection, that's the dark knowledge the student learns, even if the final hard label is just dog.
And there's this parameter, right? The temperature. That's key to unlocking this dark knowledge. How does that work?
Yes, the temperature, usually denoted as T, is applied to the teacher's outputs before they go through the softmax function. Softmax is just the step that turns raw scores into probabilities that add up to 1.
Okay.
Now, a higher temperature softens the teacher's output probabilities. It makes the distribution flatter.
Flatter, meaning less peaky, less certain about one answer.
Exactly. And this flattening effect reveals more of that dark knowledge about the less probable but still related classes. It makes subtle patterns and relationships more apparent, easier for the student to pick up on.
Ah, I see.
It essentially amplifies the signals from those less obvious connections the teacher learned. It makes those implicit relationships explicit for the student.
So like a low temperature might give you 99% dog, 1% wolf, but cranking up the temperature might give you, say, 70% dog, 20% wolf, 10% fox, showing the student the full range of related concepts the teacher knows.
You've got it. That's a perfect illustration. It really shows the student the landscape of possibilities the teacher sees.
That's really clever.
Yeah.
So it sounds like there might be different ways to actually transfer this dark knowledge. Are there different, like, types of distillation?
Indeed, there are. Generally, we talk about 3 primary types based on where the knowledge is extracted from the teacher model.
Okay.
First, there's response-based distillation, sometimes called logic-based, is the most common one.
Right.
Here, the student basically mimics the teacher's final output probabilities, those soft targets we just talked about.
Okay, the end result?
Exactly. A fantastic example is DistilBERT. It's a distilled version of the huge BERT language model. DistilBERT gets something like 97% of BERT's performance.
97%. That's amazing.
It is. While being 40% smaller and 60% faster, that technique really revolutionized natural language processing, making these big, powerful language models usable in real time, even on consumer devices.
Incredible gains. So that's mimicking the final response. What else is there?
Well, the second type is feature-based distillation. This one goes deeper.
Deeper how?
It transfers knowledge from the intermediate feature representations, specifically from the teacher model's hidden layers.
Ah, so not just the final answer, but how it got there.
Precisely. It's particularly effective in things like computer vision. Instead of just learning the final image label, the student learns how the teacher processes information internally, layer by layer. It helps the student acquire a more robust understanding of data patterns.
So the student isn't just told this is a cat, but it kind of learns how the teacher identifies the edges, the textures, the shapes that lead to that cat conclusion.
Exactly right. It's learning the teacher's internal seeing process, you could say, at various stages.
That's a significant step up in complexity. What's the third type?
The third main type is relation-based distillation. This is, well, even more advanced.
Okay.
Here, the student learns the relational knowledge the teacher implicitly captures between different data samples.
Between samples, like how things relate to each other?
Yes, it's about understanding how the teacher perceives similarities or relationships among a whole set of inputs. This might involve things like matching similarity matrices of embeddings, those numerical fingerprints that capture meaning and relationships in data.
Right, embeddings.
So it allows the student to learn how the teacher perceives connections and distances between different concepts or images.
Wow. Okay, so we've gone from mimicking the final answer, response-based, to understanding the internal processing steps, feature-based, and now even grasping the teacher's perception of relationships between data points, relation-based.
You've nailed it. It shows a real progression, right? From superficial matching to much deeper structural and relational understanding. It recognizes that knowledge in these models is really multifaceted.
It really is.
And just to add, there are also emerging techniques cropping up. Things like self-distillation, where a model teaches itself to get better.
Huh, interesting.
And attention-based distillation, where the student learns to focus on the same parts of the input that the teacher finds important.
Fascinating stuff. So, okay, let's talk benefits. This sounds incredibly powerful. When we look at efficiency, cost, accessibility, privacy, it feels like distillation isn't just theoretical. It's already fundamentally changing how and where AI gets deployed, right? What are the biggest wins we're seeing?
The benefits are truly transformative, yeah.
Mhm.
They directly tackle major roadblocks to getting AI adopted widely.
Like what?
Well, one of the most immediate and profound is just increased computational efficiency and reduced resource demands.
Yeah.
And that directly leads to massive cost reduction.
Okay, less power, less money.
Exactly. Smaller models need significantly less memory, less processing power, less energy. Think about it. DistilBERT, 40% smaller, 60% faster. That means you need less powerful hardware, less electricity to run it, and lower operational costs, including, crucially, much lower API costs if you're using cloud-based AI services. This makes cutting-edge AI actually economically viable for way more businesses and applications. Imagine slashing your inference costs by, say, 75% while keeping almost the same performance. That's a total game changer for commercial use.
That economic ripple effect is huge, I can see that. And I guess this also opens doors for just putting AI in more places.
Absolutely. That's the second major benefit: enhanced scalability and accessibility. This is really key for democratizing AI.
How so?
Distilled models can be deployed on a huge range of platforms where complex AI was just impossible before, purely due to computational limits. We're talking everything from your mobile phone to industrial IoT devices.
Right, the edge devices.
Exactly. This brings high-performance AI out of the data centers and puts it directly into our hands, enabling a whole new generation of smart applications.
Yeah.
Imagine running sophisticated AI, like directly on your smartphone for a camera app, instead of having to send your private photos up to the cloud for processing.
Ah, the on-device processing. That feels like a massive win for privacy, keeping your data right there with you, and maybe helps people trust AI more.
It really does, and that flows right into another key benefit: improved privacy and security. By letting AI models run locally, sensitive data doesn't have to leave the device. That's vital for fields like healthcare or personal finance.
Definitely.
And then there's speed. For applications that need split-second decisions, we see faster inference times and real-time performance.
Like self-driving cars.
Perfect example.
Hmm.
Autonomous vehicles need immediate responses to a constantly changing environment. Distillation means these systems can process huge amounts of sensor data with minimal latency, making those split-second decisions safely and efficiently.
Okay, it really feels like distillation is pushing AI beyond just technical tweaks. It's enabling commercial viability, wider societal impact. Is this stuff actually deployed widely now? Where are we seeing it?
Oh yeah, it's out there solving real problems. Take natural language processing, NLP, and large language models, LLMs. We mentioned DistilBERT, but also models like TinyBERT, MobileBERT.
Yeah.
They're behind the scenes in tons of real-time chatbots, language features on your phone, even on device speech recognition.
Right.
And DeepSeek's R1 chatbot, like we discussed, that's a prime example of its power. Competing with the giants, but with way less compute and cost, it's really democratizing advanced language AI.
Okay, so NLP is big. What about seeing things, computer vision,
hmm
or the devices we carry?
Definitely. For computer vision, distillation makes those heavy models for image analysis, object detection, even medical imaging, lightweight enough for faster diagnostics or just efficient deployment.
Yeah.
People are distilling big ResNets or complex vision transformers into nimble CNNs for practical use.
Makes sense.
And for edge computing and IoT devices, distillation is basically a cornerstone technology now. It means advanced AI features directly on your smartphone, your smart home gadgets, industrial sensors, all operating without constantly needing the cloud.
So my smart security camera could actually do complex recognition locally without uploading everything.
Exactly. That reduces latency, saves bandwidth, and hugely enhances privacy. Your smart devices are getting genuinely smarter and more independent, right there on the device itself.
That is a huge shift.
And it extends to autonomous systems too, like those self-driving cars. Smaller distilled models mean faster processing of sensor data for real-time decisions, detecting objects, tracking pedestrians, staying in the lane, all with minimal delay, which is literally life or death.
Wow.
We're also seeing it in cybersecurity, running AI locally for real-time threat detection, which can be faster than waiting for a centralized system. Even the big cloud AI providers like OpenAI, they use distillation internally to create lighter, cheaper versions of their models for specific tasks, cutting their own operational costs.
Right, it makes business sense for them too.
And that DeepSeek success story really underscores the societal and economic impact, showing how distillation lets smaller players compete, democratizing access to sophisticated AI.
Okay, this sounds almost too good to be true, like a silver bullet solving everything. But, every powerful technique has its downsides, its challenges. What are the hurdles or limitations here?
That's a very important point. Yeah, despite the huge benefits, there are definitely considerations. First off, there's the potential loss of nuance and accuracy.
Ah, so the student isn't quite as good as the teacher.
Sometimes, yes. Being smaller, the student might not capture all the intricate complexities of the larger teacher. This can lead to a small drop in performance on really complex tasks, especially those needing very subtle distinctions.
Okay.
There's this delicate balance, you see, between fidelity, how closely the student matches the teacher, and generalization, how well it performs on new, unseen data. Interestingly, sometimes the student actually generalizes better, even if it doesn't perfectly mimic the teacher, maybe because the process acts like a regularizer.
Huh. So it's not just about perfect copying, but learning the right things. That's subtle.
It absolutely is. Then there's technical complexity. Designing the right loss functions. Those mathematical rules guiding the student's learning and carefully tuning things like the temperature parameter, well, it takes significant expertise. It's not always just plug and play.
Right. It needs skill.
Also, data generation and quality. You need a good data set of the teacher's outputs, those soft targets, to train the student effectively. And creating that can be time-consuming and computationally intensive itself.
Okay.
And yes, there's a risk of overfitting to teacher biases. The student might unintentionally learn and amplify any existing biases present in the teacher model.
That's a huge one for responsible AI. Really critical to watch out for.
It truly is. Another major challenge, especially in the commercial world, is intellectual property, IP concerns.
How so?
Well, if you train a student model just by constantly querying a proprietary model like a big commercial API and copying its responses, that can be seen as unauthorized replication of the teacher's knowledge.
Like stealing their work.
Kind of. Major AI providers are fighting this with things like rate limiting on their APIs, other restrictions, maybe even watermarking their AI outputs. It's creating complex legal and ethical debates.
I can imagine.
And while deployment gets cheaper, the initial training costs, training both the big teacher model and the student, can still be pretty computationally heavy upfront.
Right. You still need that big teacher first. And what if the student is just like way too small compared to the teacher? Can it even learn effectively then?
That's what's called the capacity gap problem. If the size difference is too massive, it can be genuinely hard for the small student to absorb all the knowledge. In those cases, people might use teacher assistant methods, introducing intermediate-sized models as sort of stepping stones to bridge the gap.
Like tutoring the tutor first. Interesting. Okay, so distillation is one powerful tool in the AI efficiency toolbox. How does it fit with other techniques? Are there other ways to make models smaller or faster?
Great question. Yeah, distillation is one of several key model compression techniques, and they often work together.
Like what else?
Well, there's pruning. That involves directly modifying an existing network by removing unnecessary bits, redundant weights, maybe whole neurons or layers trying to reduce size without hurting performance too much. Okay, trimming the fat, pretty much. Then there's quantization. This reduces the numerical precision of the model's weights and activations. For example, changing them from high-precision 32-bit numbers down to more compact 8-bit integers.
And that makes it smaller and faster.
Dramatically smaller in terms of memory and often much faster computationally. And another one is low-rank approximation, which breaks down large weight matrices into smaller, more efficient components, reducing the parameter count.
Okay, so pruning, quantization, low-rank approximation,
Mhm.
they all make models smaller. But what's the fundamental difference compared to distillation?
The key difference is that knowledge distillation trains a brand new, smaller student model. It transfers learned knowledge, often allowing you to use a completely different, maybe more optimized architecture for the student.
Right, a new model learning from the old one.
Exactly. The others, pruning, quantization, low-rank stuff. They directly modify an existing neural network. They tinker with its structure or its numbers. Got it. But what's really powerful is that these techniques aren't mutually exclusive. You can often combine them.
Like use multiple techniques.
For sure, you could first distill a huge model into a smaller student model and then apply quantization to that student to squeeze out even more efficiency. The best approach really depends on your specific deployment, needs balancing performance, memory, speed, all that.
This has been a really, really illuminating deep dive into AI model distillation. It's so clear it's not just some technical optimization. It feels like a fundamental shift, letting advanced AI move out of labs and giant data centers and into our actual lives, making it faster, cheaper, more private, way more accessible. It genuinely seems to be democratizing AI.
I agree. Its continued evolution and how it gets combined with other compression methods, that's going to be crucial in shaping where AI goes next. It really
Yeah.
does challenge those established competitive advantages and empowers smaller players. It promises a future that's hopefully more efficient, more secure, and just pervasively intelligent. The idea that a smaller, agile team can now genuinely compete with the giants just through clever techniques like this, that's a truly exciting prospect for innovation.
Absolutely. So, thinking about all this, what stands out to you about how distillation is changing the game for AI? Something for you to mull over after this deep dive. Thank you so much for joining us on this exploration. If you want more content like this, definitely be sure to subscribe to the deep dive wherever you get your deep dives. And hey, for hands-on tutorials, more insights into the world of AI, you can check out Ian Ochieng's YouTube channel. That's Ian Ochieng, Ochieng AI. We'll be back soon with another deep dive into your sources.